to the deep dive. Today, we're plunging into the fascinating world of abstract algebra. We've got some source material here tackling a really specific, pretty tough challenge.
That's right, solving a complex polynomial equation. And complex is, well, kind of an understatement here.
Okay.
We're looking at an eighth degree polynomial. I mean, it's dense with terms, coefficients. It just looks difficult to solve using, standard methods.
Right.
So the mission for this deep dive is really to follow the surprising path this source takes. It uses a particular technique to cut through all that complexity.
And find the roots, presumably.
Exactly, to find the roots.
Okay, so let's unpack this then. Yeah. The equation the source gives us, it's pi tx by 16 by 7 plus dots plus frac 492,874,17 at 69.7.
Oh.
Just looking at it.
Yeah.
That high power, those really intricate coefficients, the sources, they come from some original values called Lortel graph.
That's the notation they use.
You just know you're not going to factor this one easily.
Oh, absolutely not. High degree polynomials like this, they usually mean incredibly complex calculations. Sometimes it's just impossible with the usual methods.
So what's the trick here?
Well, this is where the source brings in its key tool. It's called the discriminant formula of Mourad, Sultan, Ezouidi H's.
Okay, quite a name.
It is, and you should think of it less like a simple formula you just plug numbers into, and more like a specialized mathematical lens.
A lens to look into the polynomial structure.
Precisely. It's designed for that.
Yeah.
So this formula, it's applied to the polynomial's coefficients, or really those lower q values they come from.
Right.
And it calculates a new set of values. The source calls these skogallers.
Okay, skogallers. So it's like transforming the problem, putting it in a different mathematical space, maybe.
That's a great way to put it. These sources are essentially new coefficients, derived from the originals using this very specific formula.
What happens then?
And here's where the really surprising thing comes in, the discovery from the source's calculations. When they did this transformation, most of these new square values, they turned out to be zero.
Zero? Really? For such a complicated looking equation, how?
Well, that's the power of this specific formula. It seems it's designed so that if the polynomial has a certain underlying structure, maybe some hidden symmetry.
Which this one must have had.
Apparently so. This transformation sort of filters out the terms that were obscuring that structure. The source explicitly shows C where X, E where XS, C where SS, A stars, A RSS, and 6 orders, all zero.
Wow. Okay, so if you rewrite the polynomial using these new great Sarah values, I think the general form is something like PXX SSSS plus S1S6 S2RX5 plus the idea. Yeah, though the signs alternate.
Right. But if most of those phrase coefficients are zero, the equation must simplify dramatically.
It absolutely does. It's quite striking. The source gives the non-zero values it calculated. Says-4 are 336x, then 3R4, 4.6x, S4 are 21196x, and finally 770
Okay.
So you plug just those back into that.
There, you get it. You get this. 6 by 8 plus 36 by 6 plus 446 by 4 plus 2196 by 2 plus 3/3 of $465. Look at that.
Whoa. All the odd degree terms. They're just gone.
Finished.
That's incredible. From that initial messy eighth degree thing to an equation with only even powers. And that structure, well, it immediately suggests the next step they took, right? Substitute something for 6 by 2.
Exactly the move. Let 6x's by 2, 2. Classic technique when you see only even powers.
So the equation becomes what? 6, 7, 12, 6, 3 plus 496x6 plus 296x6 ton plus 346x2 plus 36x6
Right. $64 plus 46x62 plus 2196x plus $3,465. And that's just a fourth degree polynomial and $6. Much more standard.
A quartic equation. Still not trivial, but definitely something we have methods for solving.
And the source gives the roots for this 6 polynomial.
It does. And they turn out to be pretty clean integers, actually. 6x equals 3 Mohs heaven, 7/11, we get all 50 11s.
Okay, so those are the values for $6, but $6 be 6 too.
Correct. So finding the roots for the original variable, $6, is now pretty straightforward.
If $6 equals those negative numbers, $6 must be imaginary. Exactly. $6.33 means 6 data less 3n is 33, which is PMI psi.
And the same for the others. So we get the 8 roots of that original intimidating polynomial.
That's it. Sex, PMI squared of 3, PMI squared and I squared and 15.5.
Wow. 8 purely imaginary roots. And the source also shows them in a different form, doesn't it? Something involving the original Old-Ollier's 16 I size.
Yeah, that's interesting too. It presents them as frac 16 PM, I squared 3, and so on for 11 and 15.
Frac 16 PM, I squared E. It's fascinating how that initial coefficient L-Q pops back up there in the final root structure.
It really is. What's truly fascinating here for me is how this very specialized tool, this specific discriminant formula, It acts like a key.
Right.
It doesn't just brute force the solution, it unlocks the polynomial's hidden structure. It revealed that simplicity, the lack of odd powers.
Which then lets a standard technique, the x by c2 substitution, finish the job.
Exactly. It reduced this thing that looked almost impossible down to something manageable.
Yeah, it took an 8th-degree monster, applied this transformation, and found it was essentially based on a quadratic structure leading to these purely imaginary roots. Really neat.
It absolutely is. And it kind of leaves you with a thought, doesn't it? It raises this important question for you listening. How many complex problems out there? Maybe in math, maybe elsewhere.
Yeah.
How many might have some hidden simplicity just waiting to be discovered if only we had the right tool or maybe just the right perspective, the right lens to see it.